Alright, so today is day 73. I did 3 more lead code problems. I did these last 3 ones, so I finished already 3. So I'm basically half of all the roadmap. So we are at a good pace. Let's go ahead and redo them again. So for the first one, we are given a binary tree alongside with 2 lists, the traversal of the tree in pre-order and the traversal with in order. And pre-order is like the normal DFS. So we take first we visit the node and then we move left and then right. And then in order, first we move left, then visit the node, then move right. So the interesting thing is in the in order is that it has like a geometrical interpretation. So if we see a node 1, it means that the left successor is going to be to the left and the right successor is going to be to the right of the array. So this is going to be like a usual observation that we're going to use to build the solution. And the other observation is that we can visit the nodes in the pre-order way. So I visit this node, the 1, then I search the child here. I mean, in order to know where the child is, I need to get where the 1 is located in the in-order array. So I need some sort of dictionary that maps the node value to an index. And then perform again DFS over the left value, but it's going to be bounded. It's going to be bounded because, for example, the 3, I know that this left child is going to be to the left and the right child to the right, but the left child, it has not left child because we know that 1 is the successor. So let's say that the left boundary is going to be bounded by the right boundary of the predecessor. And we can compute it if the function, we pass a function that depends, that the node gives the next, determines the child, its boundary by giving it to him. So I can say build and I pass low and high. And I can, let me think about it. Okay, first I need to know the index base of the in order. So I'm going to create a dictionary to map a vertex and the index for I, b in enumerate in order. And then I need a variable to keep track of the nodes that I'm constructing from the tree. So the first thing that we gotta do is the stopping condition, which is gonna be if we are trying to search what happens to the thing is like we're gonna move the boundary at every iteration, and the boundary it's gonna be determined by the father. So and this one is gonna be moved by the 1 step, right? So if I'm at the left, I'm gonna move the right 1 step to the left, and if these ones, and if the high boundary is if the lower boundary is higher, so it's more right to the left boundary, to the low boundary, then it means that we need to stop. So I'm gonna say if low greater than high, then we gotta stop. So I'm gonna return none. If not, we need to retrieve the value so we can create the node, and this one depends on the pre-order. So I'm gonna say pre-order, and we do it at the iteration that we want, and then we update the value, so it's plus equal 1. Then we create the actual node, so I can say tree node and I pass the value. And now we need to make the connections, so I gotta say root.next, but these ones are gonna depend on, we gotta give the boundaries, so it's gonna be low and mid -1, and this is root left, then root right, it's gonna be build mid +1 comma high. And now how do we compute mid? Essentially it's searching the node in the dictionary that we know, because the dictionary maps it to the list. to the in order list. So we can do this. Then we can return root, because in the problem we gotta return the first element. So I gotta return build, and build that the first iteration is gonna be the whole array, which is gonna be between 0 and length of in order -1. Okay, I forgot. Here there should be a comma. And pre-I should be non-local. Pre-I. Okay, good. I'm gonna solve one problem more. Let's go. For this one, binary tree maximum path sum, we're given a tree. Every tree has, we know that a node has a value, and we gotta find a path that has the highest sum. And we could be given even negative numbers. And a path, it's something that it's like a chain, so it does not branches out. That's it. To solve this problem, we can. It's very similar, I would say, to some sort of. What was the name? What was the name? Bellman. I think it's called Bellman. Because the optimal path at this node depends on the optimal at the next node. That's the main intuition in this problem. And the thing here is that we can have, for a given node, two types of path, which is the one that branches or the one that does not branches. The one that branches does not consider the predecessors in the sum, and the one that branches can return its value, so it's get computed globally. So first we need a variable. I'm gonna initialize it as -infinity. Okay. Then we need to run DFS, and to run this DFS, how are we gonna do it? How do we compute the maximum? We have 3, 2. Okay, I think I got it. I mean, as always, we pass the root. If not root, we're gonna return 0, because this is the optimality. Because if we have none, then it's 0, and then we're gonna have some sort of condition that is gonna be 0 plus something, right? And we want to compute like the sort of, for a given node, in this case if we are at 1, how much does the sum can get if I take both 2 and 3 into account. So we're gonna have a left gain, and this gain is gonna be equal to the sum of the node value. Wait, it's gonna be the maximum, because if the right gain, I mean the left gain in this case, it's negative, and we know that by recursion this is gonna start at the end. I mean, when it returns value, it's gonna be at the end of the node. Then we know we don't want to take it, so we would rather return 0. So I'm gonna say, I think this problem is, yeah, I would say it's hard. This problem is hard. I thought it was medium. So we gotta return the maximum between running the maximum in the right node, in the left node. So it's gonna be root dot left and 0. We'll do the same for the right. Maximum between running DFS in the right and 0. Then we can update the gain. So we are saying we can have a path that has this nature of it branches out at the current node that we are. So it's gonna be node. It's gonna be the best, which is the max between the best at this point and the best that we are computing now, which is gonna be node.val plus left gain plus left gain plus right gain. Okay, now we have to return back like what would happen if this is not the case. Then we're gonna return back just a single branch, and the best single branch is the one that yields the maximum sum. So it's gonna be just simply return node.val plus one single branch. So in order to choose between 2 and 3, we gotta choose the max value between 2 and 3, which is gonna be the gain at the right and the gain at the left. So I'm gonna say left dot gain and right gain, and we gotta run the fs, and we gotta return best, and we're gonna make best as a non-local variable. Node is not defined. Do you mean none? Okay. Rate limit exceeded. Okay, now it works. Yeah, this problem was quite hard, but I believe the previous one was also quite hard. And there is one more, but I'm pretty tired. I think it's not worth it, this one to do, because it's just to serialize a binary tree. And the order to serialize it is you can run BFS over it. And BFS is very common. And then to deserialize this is just you use also like a queue, and yeah, and keep track of every node and make the connection based on the queue. You pop left, you take the value, make the connection, the left and the right one, and do it again. Yeah, I think this one is not worth it. I think what makes this one hard is just keep track of the annoying things, like the how do you separate it, how can you decode it back again, how do you split the string, and so on. Alright, so that was it for today.